Hello everybody, Mr. Hasty here. Today we're going to be starting on 12.2, which is on the ideal gas law. So, the core concept here is last section we learned to relate the information of a gas with itself as things change it. So we learned that the combined gas law says that P1V1 over T1 equals P2 V2 over T2, meaning that you can know the information about a gas, change some of the facets, the pressure, the volume, or the temperature, and figure out how that gas is going to change. But is there any way to predict that information for a gas, or must it all be measured? Well, it turns out that they developed something called the ideal gas law that will allow you to predict certain information for a gas if you know the other information. So we have to go through a few steps to get there first. The first thing we're going to talk about is Avogadro's principle. This is the same Avogadro, of course, from Avogadro's number. He speculated that any gas at the same temperature and pressure was going to contain the same number of moles. So at equal pressure and temperature, gases will contain the same number of particles. And this is pretty crazy. That means that a gas that is very, very light, like helium, which in our environment is just number of particles, which is just single helium atoms, and a gas that's very heavy, like sulfur hexafluoride, given that they're at the same pressure and temperature, right, an equal volume of gas will contain the same number of particles. Now, to regulate this and to have a conversation, we have something called standard temperature and pressure, and these are just benchmarks that we use. Standard temperature and pressure means that we are assuming it's a 0 degrees Celsius, 1.00 atmosphere environment. So whenever I say STP, we are assuming these two things to be true. Now, we talked about molar mass earlier, and for gases we're going to have something called molar volume. The molar volume is the volume a volume 1 mole of a gas takes up at standard temperature and pressure. So it turns out that just like we can have a molar mass, 1 mole of a substance is going to have this mass. For gases, and this is particular to gases, 1 mole of a gas is going to have a particular volume. Furthermore, it was discovered that 1 mole of a gas at standard temperature or pressure is going to equal 22.4 liters. That's going to be a key ratio, kind of like Avogadro's number was a key ratio for us when we did our basic stoichiometry. So 1 mole of a gas is 22.4 liters. And it's really important to keep in mind that that's at standard temperature and pressure. All right, so let's do a few conversions using that. So just like we had that triangle for doing mass to moles, moles to grams, and things of that nature, we're going to have a triangle here. And that is the following. We are going to be able to take volumes and go to moles, and then moles and go to mass. Now, to go from mole to mass, we're going to again use the molar mass from the periodic table. This is where you have to add up the different elements in the substance to get the mass of 1 mole. If it's a singular element like krypton, you can just use the atomic mass number off the periodic table. But for carbon dioxide, you have to add up 1 carbon and 2 oxygen. The volume is going to be based on the ratio that we got previously, 22.4 is going to be our conversion factor there. So let's start with number 1. What volume would 1.20 liters of sulfur hexafluoride take up? So, I goofed there. It's supposed to be 1.20 moles. Because if you notice, liters is already volume. So if we start with 1.20 moles, and we want to know the volume, to go from moles to volume, we're going to use our 22.4. So it's really important we understand how that works. It's 22.4 liters per mole. So the 22.4 is going to go on top, liters, and the mole is going to go on bottom. Cancel our units and do our calculation, and we get to 3 sig figs, 26.9 liters of sulfur hexafluoride. Notice that there was no conversation about the fact that we had to look particularly at gas, because at standard temperature and pressure, Avogadro's principle guarantees us that we can convert volume to moles. All right. What would the mass of 1.4 liters of carbon dioxide be at standard temperature and pressure? So we're starting with 1.50 liters. That would be a volume. So we're here, and we're trying to get to mass, which is over here. So the first step in that process is to go from volume down to moles. So we use the conversion rate, but we have to use it upside down this time because we want our units to cancel. So it's 22.4 liters is 1 mole. Cancel, cancel. Now, if we did this right here, it would tell us how many moles of carbon dioxide we have. But we want to know mass. So 1 mole of carbon dioxide. And this is where we have to break out our periodic table. This is where you have to look up 1 carbon plus 2 oxygen. And when you do that, you get 44.009. That would be grams. So we go through the process, multiply the top, divide by the bottom, and we get to 3 sig figs, 2.95 grams. Now, next thing is we have one going the other way. We start with a volume. It's really important to notice this volume is in kilograms. And our setup is based on grams. Molar masses is based on grams. So instead of calling it 1.24 kilograms, remember, to go from kilograms to grams, you multiply 1,000. That's 1,240 grams of octane. And we're trying to get to volume, so we're going backwards. So the first thing I have to do is find the mass, molar mass of octane. Octane is C8H18. So that means you have to add up 8 carbons, 8 times 12.011, plus 18 times 1.008. And that's going to come out to be 114.232 grams of octane in 1 mole. But we don't want moles, we want volume. And 1 mole of any gas at standard temperature and pressure is always 22.4 liters. We do the conversion here. And we get to 3 sig figs, about 243 liters. So that's the kind of converting we're going to need to be able to do, go from moles to volume to mass and back and forth. Okay, so let's actually get into the ideal gas law now. So before we do that, what we have to understand is where the ideal gas law came from. The ideal gas law came from a combination of the combined gas laws along with Avogadro's principle. They basically started to put all those equations together and realized that it needed a slight adjustment. And that slight adjustment is a multiplication by what's called the ideal gas constant. This is like Planck's constant or pi. It's a number that's in there to make the mathematics work out properly. And it was a number we discovered based on all the relationships we found. Now, what units you choose to use can affect the math greatly. So we're going to be very specific in the units we use here. The ideal gas constant, which we're going to call R, is going to be equal to 0.0821 liters times atmosphere divided by moles Kelvin. So there are other numbers. For instance, it's also 8.314 liters per kilopascal over moles Kelvin, or 62.4 liters per millimeter mercury divided by moles Kelvin. But we're going to try to do everything in terms of atmospheres, Kelvin, and liters. If we stick to those units, we don't have to worry about a bunch of different numbers. We just have to worry about one. So the ideal gas law says that the pressure of a gas times the volume of a gas is equal to the number of moles. So this is a new one. The N represents number of moles times the R, which we just defined as the ideal gas constant, times temperature. That relationship is true for any gas. Now, we'll talk later about the term ideal versus actual in practice, but this will give us good predictions for that information. So let's go through a couple examples. Calculate the number of moles of ammonia gas contained in 3.0 liters at 300.0 Kelvin and 1.50 atmosphere. So one thing that's really, really important to notice here is the fact that it's ammonia gas is not actually going to matter for us. Any gas is going to work the same way no matter what type of gas it is, if it's a heavy gas or a light gas. So let's start doing it. Well, pressure. Calculate the number of moles. We have 1.50 atmosphere. That's a pressure. So I'm going to fill that in. Volume. 3.0 liters. So we're going to put 3.0 here. Equals N, number of moles. Well, that's what it's asking us to find. So that's going to be our variable. R is always going to be 0.0821 for us. Times your temperature in Kelvin, 300.0. So, just like you've done before, basically we're going to divide both sides by everything that's not our variable we want. 0.0821, 300.0. Divide, same thing over here. Try to fit it in here. Now, as we do that division, what's really important to remember calculator-wise is you have to put the multiplication on bottom in parentheses. If you put it into your calculator incorrectly, it will not read correctly. So when you do it, you need all this to be in parentheses. Otherwise, your calculator will goof it up. So when I did that, I got 0. Let's see, sig fig restriction here would be 2 because we have a 3.0 liter. I got 0.18, but 0.181. Well, this is asking for number of moles, so clearly number of moles. That one's done. Let's look at the next one. Calculate the volume, so we're looking for V, of 0.850 moles of oxygen gas at 273.0 Kelvin and 1.00 atmosphere. So the pressure is 1.00. We don't know the volume. We know the number of moles is 0.850. The R is always 0.0821. And we're at 273.0 Kelvin. Now, if we look, this is just 1.00 times V. That's just V. So all we have to do is the calculation on the right-hand side, which is pretty straightforward. And we have to restrict ourselves, in this case, to 3 sig figs. And I get 19.1. But 19.1 what? So this is where understanding that we're using this ideal gas law. This ideal gas law guarantees that volume's always liters, pressure's always atmosphere, moles are always moles, and temperature is always Kelvin. So we can always rely on this to tell us what our units are going to be. In this case, a volume is always measured in liters. All right, guys, that's going to end our discussion for today. See you guys next time.